All right, good morning. Hope you all are doing well. So last time we started looking at the basic idea behind a binary file. And we said that when you're dealing with the file in binary mode, right, that you're really dealing with the file in terms of how the data is actually really physically stored. So we're very familiar with things like ASCII, operating with the file in ASCII text mode, where we, for example, might think of the file in terms of storing, names where each name is separated by a line return character, or maybe it's storing a bunch of numbers where each number is separated by a line return character. But in general, there's going to always be some sort of special delimiter that's going to distinguish one data value in the file from the other. But when we process a file in binary mode, we're really thinking of it in terms of how the data is really physically stored, because in the end, everything is binary, everything is ones and zeros. And that's the way in which we ultimately have to think about the data when we're operating with the file in binary mode. And so we started to look at some of the pieces here in terms of using a binary file towards the end last time. We started talking about the issue of flags. So when you create your file object, in addition to saying what the name of the file is, you can also specify one or more of those flags. And we looked at a few of them, such as iOS in, iOS out, and then iOS binary, which is the flag that you use to indicate that you're going to be processing the file in binary mode rather than in ASCII text mode, which is the default mode. So without the binary flag, then that means we're just treating it as an ASCII text file instead of as a binary file. And again, it's a different way of thinking about things, because with the text file, we say things like, well, I'm going to read until I encounter a line return character. And that's how I'm going to read in, one number at a time and distinguish one number from the other numbers, or maybe one name from the other names. But there are things that come up as a result of doing that. So for example, in some of the previous assignments, some of you may have had to do a little bit more to get the file reading to work because of differences, for example, in how Windows handles a line return versus other operating systems. But with a binary file, we're not reliant upon things like handling a line return, because in a binary file, we don't have to have a delimiter. We're just going to have the data itself, but as long as we know in general what kind of values we're storing in the binary file, then we have a way in which to distinguish different data values from one another. So if we could have a file storing a bunch of letters, and because that's a known size, right? So meaning a letter like the letter A, for example, that's a byte, which corresponds to type char. And since that has a known size, right, we can work from that to grab, a certain character and, bring it into the program, for example, and see out it or whatever we want to do with it. Or we could store numbers, right? We could have a file storing, for example, integer type numbers. And again, that's also a known size that we can work from. So we would still have a way to distinguish one number from the other. So that's the key thing with a binary file. Certainly, in order to use the file correctly, we need to have some idea of what's being stored there. Because as we hinted at last time, when we talk about reading from a binary file, right, there's really two key things that are going to come up. How many bytes are you going to read, and where are you going to start reading those bytes from, right? And then that's it. So where are you going to start from, and how much are you going to read? Of course, to process the file in a meaningful way, we have to make sure that we're, if we're wanting to get the second number in the file and read that into an integer variable in the program, well, we need to make sure that we go to the right place, because if we go to the wrong place, then we're not going to really be able to get that second number. But the idea is that you can really think about the file itself now like an array, right, in terms of byte numbers. So the file is organized into individual bytes in terms of byte 0, byte 1, byte 2, right, up to byte n-1. And then we'll also see along the way the issue of encountering the end of the file. But the idea is if you do a read operation, and let's say you read in the last value, whether it's a character or a number, and then if you do another final read statement after that, then that's going to take you to what we call the EOF, right, or the end of the file. And there's ways to check for that, because there's actually a flag called EOF bit that will tell you whether you've, through your read operations, whether you've reached the end of the file or not. And we'll eventually encounter that when we talk about things like how you can go directly to a certain byte, and what you can do if you end up reaching the end of the file, but then you still want to go back to somewhere else in the file after that. But that's the idea. So a different way of thinking about some of these operations, certainly. So whereas we use things like the greater than operator, or the less than operator for input and output with files in ASCII text mode, and that worked because of how those files were being processed. In particular, we were working off of things like delimiters. With the binary file, it's different, right? The way in which we think about reading and writing, because we have to think in terms of at the byte level. But we do have functions called read and write that are designed to work with the file that's being processed in binary mode. And we started to look at the basic idea of that towards the end last time, where we said that if you had a file that was storing different characters, meaning like maybe capital A, for example, capital B, and you wanted to read, let's say, the first character from the file and store it into this variable of type char in the C++ program, then we could do that with a statement like this. So f_object.read address of C, comma, size of C. So the size of operator, that in C++ can tell you the number of bytes of whatever it is you're working with. So we can apply the size of operator to a type, like size of int, right, or size of char. We can also apply it to a variable name as well. And the idea is it's going to return the number of bytes, right? So in general, we don't usually want to just hard code that, because the size could vary across different systems. But size of is going to tell you for the system that you're running on, in this case, how big a char is. Or if we applied it to an integer variable, then it would tell us how big that integer variable is. Because the second argument for read is telling you how many bytes, right? How many bytes of data to read from the file. The first argument, which you'll notice we said address of C, is telling you where to put it, right, in terms of memory. Because when we do a read operation, we're reading from the binary file into memory, right, into some variable. And now, assuming that we just opened the file, right, so, and we showed different possible ways of potentially opening the file depending upon what mode that we want. But let's just assume, for example, that we did something like this line here, f_object.open, name of the file is numbers.dat, so a data file with the 3 flags in, out, and binary. And then right after that, we did the statement f_object_read. Well, we're currently at the beginning of the file. And so with this first read statement, in terms of file position, that's where we're going to be at, is the beginning. And we also know that we're wanting to read 1 byte, since that's the size of C, which is a variable of type char. And we know that where we want to store it is in the C variable, right? So that's why the first argument is the address, right? The address of C, because the first parameter really, the first parameter in this read function is really a pointer of type char star. So the first argument is going to be treated as the address of a character type. And so that's going to read 1 byte from our binary file into the variable C, right? And then the idea being that from there, we can use C to do whatever we want with the data, right? So for example, if we want to, do C out C, we can do that. And if we want to, keep reading, then we could potentially think about maybe setting this up in terms of a loop, which we'll see here in a bit with our code examples. But that's kind of the starting point here. And the write function is also, fortunately, again, it's also called write. So function names are just read and write. And the write function also has the same general setup as the read function, meaning the same 2 types of arguments. So the first argument in the write function is going to be the address of a variable. In this case, the address of the variable that you want to take the data from and place into the binary file. The second argument is the number of bytes that you're going to be writing. So we can also use the size of operator to do that as well. For example, fObject.write address of C2, comma, size of C2 could be used to write this 1 character, in this case, the capital B, to the binary file. And again, assuming that whenever you do a read and write, it's going to advance what's called the file position. Although there's ways to change that. We'll eventually look at the seek functions, which can be used to go to a certain position in the file and do a read or write operation at that specific byte location. But here we started out in the beginning, we read the first value there, and now we're going to write the value of the B here after that in the file. So we still need to say address, address of whatever variable for the first argument, and then size of that variable is what we can put for the second argument, because that's specifying the number of bytes. And really the idea behind all this is we're saying that because the implication is that if you're doing something that's not a character directly, like integer, for example, or maybe even a structure object, which we'll start to see, all those things are possible, but nonetheless, the type of the first argument here, it has the type basically char star, right? Address of a character type. And so it just means that if you're dealing with something that isn't a character directly, we're just going to, in the end, we're going to have to cast it to that type of char star. So we'll see that situation come up as well. And then again, the second argument is just the number of bytes that you want to read or write. Okay, so that's the basic idea in terms of reading and writing. And now, if we wanted to do something like integer, because really anything is possible. And in fact, one of the nice things that that we can take advantage of here is when you think about things like arrays, for example, or maybe a structure object. Um, so far, we've been thinking about everything in terms of doing it step by step, basically, right? So in the case of an array, doing each individual element, right, processing it separately, or if it's a structure object, processing each field separately using the dot operator. Um, right, and because that's what we have to do when we're dealing with the file in ASCII text mode. But given the way that binary files work and the fact that we're really just grabbing, we're just grabbing a sequence of bytes, when we're working with the structure that we know is going to ultimately be stored together in memory, such as an array or the fields within a single structure object, or maybe even an array of structure objects, the idea is we can grab all the bytes, right? For example, for the entire array, assuming we want to build the array from the contents of some existing binary file, and with just one call to read, right, you could populate that entire array. Because we're seeing here that with both of these functions, again, all you have to really say is, how many bytes total are you going to be reading or writing? And then what variable are you working off of? Meaning what variable are you taking the data from, if it's a write operation, or what variable are you bringing the data into, right, if it's a read type operation. So the idea is that, certainly the name of an array could be used, for example, in these arguments as well. And so instead of having to individually, loop through and read to each index in the array, you can just do it in one go, right? Given the fact that the entire array is stored back to back in memory. So if you have your file organized already to where each, value is a different number, and then you grab the right number of bytes from the beginning of the file, well, then you're just going to read that in as one big block right into your array. And likewise, to do a write operation, if we've populated the array in the program with values, and then we want to write that entire array to a binary file, well, we could do that also with one call to the write function. So again, that's another advantage of binary files, is we can, at least when we're dealing with structures that are stored together in memory, which includes things like the fields within a single structure object, or an array, including things like an array of structure objects. When we know that all the data is going to be stored together in memory, then we can take advantage of that, right, in terms of how we use things like the read function and the write function. Now, I mean, if you're doing things like building a linked list from a binary file, it's not quite the same as an array, because we know that the nodes of the linked list are not themselves all stored back to back in memory, right? Going back to all of our discussions throughout chapter 18. But, that's another example of something that's possible, right? To take the contents of, so maybe, your binary file is storing student records, right? That would correspond to the different fields of the student structure that we defined, meaning each record is storing a name, and we'll see that we'll re-implement that structure slightly differently when we're working with it in terms of binary files, because instead of having the name field as type string, we'll actually have it as a character array. So that way the size is fixed, because that's going to be important in terms of working with a binary file. But if you're wanting to do something like that, like your binary file is actually storing a bunch of different student records, meaning each record has a name, an ID number, letter grade, and test score, we know that the nodes in the linked list themselves are not going to be stored together in memory in general, but the individual fields within a single node are stored back to back. So you could still grab, for example, the whole first student record, read that in one go into the first node, right? And then, create the next node in your linked list, read the second record, put the data in, pull the data into that node, and then, form your connections. So with something like that, you know, we would still end up having a loop to build the list from the different records in the file. But it would be, you could do also just one read call per node, right? So you don't have to do like a separate read for getting the name or getting the ID number, getting the letter grade or test score, right? You could just do one read call per node to populate that node, and then keep looping, right, for however many nodes you want to create, and then connect that list. So that's another example of something that we could do as well if we're wanting to build a linked list from, you know, an existing binary file. So really anything is possible, because the, you know, the type here doesn't just have to only be a char. But the idea is that in terms of binary, your baseline level is a byte, which means 8 ones and zeros together. So when we talk about a bit, because you know these terms come up a lot in the 260 class, but when we talk about a bit, that means a 1 or a 0. And when we talk about a byte, that's 8 of those together, right? So a grouping of 8 ones or zeros together. And that's our baseline, right? Everything kind of is derived from that. So for example, an integer, when we talk about an integer, that's on most systems, right, just 4 bytes together. So 4 of those bytes together for a total size of 32 ones or zeros, right? 32 binary bits. Or a short, for example, is smaller because that's only 16 bits or 2 bytes together, which we usually call that also at the assembly level a word. And then integer is what we usually call a D word or a double word. But everything is derived from that baseline of a byte. And so that goes back to the idea behind the read and the write functions. So the type there is, for the first parameter, is a pointer basically of type char star, because char corresponds to byte, right? Meaning 8 bits, which is our baseline. So the idea really is that when we are wanting to talk about something larger, like reading in an entire student structure object or reading in an integer, that's fine. But because byte is still the baseline, that's why the type of this first parameter is always treated as char star. And so what's going to happen then is if we want to do something else, then we're just going to cast it to that pointer type, meaning to type char star. So if we wanted to do something like with an integer, let's say, instead of a character, then the difference in terms of how we would use the read or write function would just be that extra bit for doing the casting. So a little bit lengthier, because we'll see this this thing come up a lot with some of the examples. So in this case, we have this integer variable x storing the value 27. And then at some point, we're saying that we want to write that to our binary file. Well, we can't just simply say address of x by itself, because that alone would be type int star, right? Meaning either, you know, pointer to integer or address of integer. But we need the first parameter here to actually be char star rather than int star. So we just take that. We do still say in this case that we still use the address operator, because we're talking about the address of x rather than the value of x, but we need to cast it to type char star. And so that's where this reinterpret cast can come into play and help us out here. So that cast in particular can be used to cast from one pointer type to another. So what we're doing, the extra thing that we're doing there really is just casting from type int star to char star. And then the second argument is just similar to before, right? That's just still size of, and then the name of the variable that we want to apply it over. And again, when we talk about a byte, because we do want to think about the data actually in its native binary form. When we talk about a byte, we just strictly mean that a sequence of 8 ones or zeros together. But an integer, when we think about type int in C++, that needs to be in general larger, right? Much larger than a byte. Because in the 260 class, you'll talk a lot about hexadecimal, binary, how to do all the conversions from binary to decimal or decimal to binary, binary to hexadecimal, and so on and so forth. But for now, we'll just say that, if you only had 8 bits to work with, the largest value that you could ever possibly make would be 255, right? Meaning the number 255. And in general, when we're doing operations with numbers, right, certainly we need to be able to go much higher than that. So the fact that an integer is 4 of these bytes together for a total of 32 bits means that our, the range of numbers that we can make is much, much larger, with the largest possible value being a little bit over 4.2 billion. Whereas if we're talking about things like storing characters, like storing an A, a B, a C, we only need 8 bits to make that. So that's why in general, right, we have different, at least at the high level language level, like C++, why we have all these different types where some types take up different amounts of memory compared to others, right? Because an integer in general needs to be able to go much, much higher than something of type char, right? Which is why we don't usually use type char for mathematical, types of operations in a program, and instead use things like integers or perhaps doubles if they, need to be a floating point number. But char corresponds again to byte, which is our baseline. And so that's why the type here of the first argument is char star. But again, if we are working with something else, that's fine. We just need to cast it to that type. So this is the same idea again, except we just have the little extra bit that we have to put here with the whole cast operation. But the intent is the same as what we were doing before. So this means take whatever is an X, which in this case, we're saying it's the number 27, and write it to the current position that we're at in the binary file. That's what we're saying with these two arguments here together. But the difference is, whereas something like this, because if we're actually thinking about the binary file in terms of how it truly, what it truly looks like, when we get right down to it, right, it's not really the letter B per se, but it's the binary sequence that makes up the letter B. And likewise, when we think about the data for X here in the binary file, it's not what we think of as, right, 27, but really the binary representation of the number 27 as a 32-bit binary value. So when we write this to the binary file, what we're really writing is this is a sequence of 32 ones and zeros that corresponds to the value 27 in such a way that if we later go back to that same position in the binary file and we read those same 32 bits and maybe put that into another integer variable, and then, for example, see out that integer variable, then we're going to see the value 27. So that's the basic idea. And so anything here is possible in terms of what we might want to store and how we want to use it, as long as we correctly set up things like our read and our write function calls. And we haven't yet got into all the details as far as going to a specific byte, right? So far, we've been just kind of looking at the basics of the read and the write functions. But beyond that, we do also have the ability to control where within the binary file we're going to read from or write to. Because we may already have built up this big file storing whatever types of values. It could be a bunch of integer numbers, it could be a bunch of characters, it could be student, structure object data. And we also in general want to have the ability to maybe just read one value as opposed to always having to read the entire file from start to finish. So beyond just these read and write functions, as we'll see, we also do have the ability to go to a certain byte within the file and then read from that point. So if we have a bunch of numbers, for example, stored in the file, we have the ability to go to where the second number is and only read that into our program, or go to where the fifth number is and only read that in. So we'll eventually see how you can combine what are called seek functions with your read or write function calls to have that control in terms of where you're going to do the reading or where you're going to do the writing. But in terms of the binary file itself, and how we can think about it, because in general, when we start working at this level, and so in this case, we said our file was maybe called numbers.dat or maybe letters.dat, for example. When you actually open the file, you're not going to necessarily actually see all the text that you might be used to seeing when you're working with the file, meaning when we've done, the previous assignments, whether it was the boy names and the girl names or the baseball teams and so forth, when you open the file, right, you were able to actually look through the text file and actually see all the data that was there, right? And then you could run the program and try to confirm that it was correct by, comparing it against what was in the file. But with a binary file, when you actually open the file, say in Notepad, you're not necessarily going to see everything, right? Because now you're dealing with the data in binary mode. But the way that we can confirm data is through the program, right? And you'll start to see that in your binary files assignment. But one thing that you will notice is that when you open the file in general, you're not going to actually see all the words there, but you will see it when you actually run through the program and, for example, go to that location and read that record in. But the way that we really want to think about things now is in its true binary form. And so, anything is in general possible, but we said that one thing that you might want to do is store maybe a bunch of numbers, for example, in your binary file. And that's fine, but the idea is that each number is then going to be, assuming we're talking about integers, is going to be 32 bits. So when you think about the actual file itself, we have to think of it from that, frame of mind, that the file is organized. If we're storing a bunch of numbers, then basically the file is divided up into all these different groups of 32 bits, right? 32 bits for the first number, 32 bits for the second number, 32 bits for the third number. Or if we want to talk of it in terms of bytes, then we would say that 4 bytes for the first number, right? 4 bytes for the second number, 4 bytes for the third number, because a byte consists of 8 bits. And so when we think about the file itself, we can think of it as, on some level, a big array. And because we hinted that it is going to be possible to do things like go directly to a certain value in the file. And if it's a file of numbers, then we can go to a certain number and read in only that number without having to read any of the other numbers first, right? So like an array, we have that random access, being able to randomly go to any specific byte location in the file, read that without having to read everything that comes before it, right? So more like an array as opposed to a linked list, because you can go directly to any byte within the binary file without having to read everything that comes before it. But when we think about the file itself, we have to think of it as a bunch of ones and zeros. Now we're going to be adding a little bit more here, right? The file itself would really just have the actual ones and zeros, but just to make this a little bit more clear here, we're hinting that you can think of the array in terms, or you can think of the file in terms of an array. So for example, byte 0, that would be the very, very beginning of the file. And if this file here is storing a bunch of integer numbers, then that means that in terms of how we would interpret and work with the file, we would take the first 32 bits in that file, and that's what we're saying is the first number. And again, we'll do some extra things here. I'll put some spaces here between some of these bits, because there's going to be a total of 32 of them for each number. But we'll just say, for example, that the first number in the file is the number 1, which this is what that would actually look like as a binary number. So this is a 32-bit binary number that represents the number 1. Now, in the actual binary file itself, right, the only thing we would have would be the bits themselves, and there also wouldn't be a space there. We're just putting that in between each byte. We're just putting a space there just to make it a little bit easier to read it. But so this whole thing here that's highlighted, right, that altogether is the first number. In this case, the number 1 as a binary number. Byte 1. Notice also that, like an array, we're starting our indexing system here in 0 instead of 1. So we'll see that when you use those what are called seek functions, that the indexing also starts at 0 rather than 1. So the first number, in other words, in the file is the number 1, represented as a 32-bit binary number. And then here we'll say that that the second number is going to be the number 2, which is going to look like this. So this these 32 bits together is the number 2 in binary. So that's our second value at index 1. We'll make this let's say 3 here. So that's going to be the number 3 in binary. And then we'll make this number 4. So something like that maybe as a starting point, right? So 4 numbers here to begin with. Now, there's actually a little bit more detail here because each of these values is actually 4 bytes, but this is the first record, right? This is the first number or record. This is the second one. This is the third one. And then this is the fourth one. Now, the idea in terms of the physical position within the file is we do have to take into account how big the data values that we're storing actually are. So this one here, because byte 0 corresponds to the very beginning of the file, which is where this number starts. But each of these numbers is a total of 4 bytes. So the second one here is going to be at 4, right? And so forth. They're going to be in increments of 4. Now, if we were storing characters like, type char values, then it would be, each one would just be taking up only 1 byte. But if it's numbers, then they're each going to be taking up 32 bits or 4 bytes. So really the first number is going from 0 to 3, right? Second one is 4 to 7 and so forth. Just like we talked about with arrays in memory, right? When we said that an integer is 4 bytes, but now we're applying that concept to the actual binary file. And so that's assuming we have a file with 4 integer numbers, then that would be the layout in terms of the bytes, right? 4 bytes for each number. In particular, the first number starts at byte 0, the second number at byte 4, the third at byte 8, and the fourth at byte 12. And so when we talk about reading the first number, because remember we said that with the read function there, no matter what type you're using it with, the important thing was that the first argument was saying what you're going to be, in this case, what variable you're going to be reading into. And then the second argument was talking about how many bytes you're going to read. So that's why, for example, this size of is so important here, and that we apply the right argument to size of, such as size of int or size of the x variable, because if the goal is to say read in these 32 bits that make up the number 1 in this case, and we want to read that into one of the integer variables in our program, well, we want to make sure that we grab exactly those 32 bits. And so the idea is, as long as we're at the beginning of the file, right, when we actually encounter that read statement, which if you open the file, by default, you're going to be, your file position is going to be at the beginning, unless you use a specific flag that can change that. But by default, when you open the file for the first time, you're going to be at the beginning. So we can do things like read each record in the file by just doing a bunch of reads right back to back. So the idea is if we open the file and then do a read type operation similar to what we did up here on this line, since the file position is at the beginning of the file, and since the size of x is 32 bits or 4 bytes, and since x is the variable that we want to read into, it means exactly that, right? Read in all 32 of these bits and put that into x. So that would have the effect of storing 1, right? What we think of as the number 1 in the x variable. But this is how it's physically written out, right, in the binary file. So the number 1 as a 32-bit binary value. And the idea is if we do, like, let's say we were doing this in a loop maybe until we reach the end of the file. Well, the idea also is that when you do a read operation, it's going to automatically advance the file position by however many bytes that you just read. So we just read a total of 4 bytes, which means 32 bits. And that also is going to have the effect automatically of moving the file position up to the next byte, right? The first byte that we haven't read yet. So by the time we would do the next read statement, we would already be here, right, at byte 4. So meaning if we did, if we did another one of these, and we'll just look at doing it separately here, but you could certainly generalize this in terms of a loop. If you did it the first time, and we're assuming that this is coming right after, let's make this read actually. Assuming we're doing this right after opening the file. So the first time that we do it, right, it's going to read 1 into X. If we do it again, it's going to read the 2. So on and so forth, right? This will read the 3 into X. And then if we did it a fourth time, that would read 4 into X. If we did it a fifth time, actually, assuming that's all we have in the file, if we did it a fifth time, because this is what will often happen in your loop, is you'll actually go essentially one past the end of the binary file, because that's what has to happen to actually reach the true end of the file, right? Is you would have to do one final read operation after reading all the actual data values. So if we just do it 4 times, then what happens is we read all the values one by one into X. But if we actually do it a fifth time, then what that's going to do is that's going to reach the true end of the file and also set that EOF flag, that end of file flag, to 1 or to true. Because when we do this in terms of loop, that might be one way that we control the looping, is we just keep going until the end of the file has been reached. So kind of like with an array, we oftentimes say things like keep going until I becomes equal to size, because we know that the last actual index in the array is size -1, but I has to actually get up to size itself to actually solve the loop. In somewhat of a similar sense, to reach the actual end of the file, and in terms of setting that flag to 1, you have to do one, a final read statement after reading the actual last value in the file itself. So again, if we only read 4 times and stop, that is going to successfully read all of the entries in the file, but that's not in and of itself going to set that, it's not going to set EOF to true. But whereas with the loop, that's usually going to happen, because that's going to be the stopping point for the loop. So that's why we mentioned this one here. So in this case, the last one's actually not going to, it's not going to actually read anything because there's nothing to read. But it is nonetheless going to set that EOF flag to true, because we will have reached the end of the file at that point. Okay, so that's the basic idea. Now, we also talked about the issue of seeking, though, right? And reading maybe just a specific byte. And the idea is in order to do this, we do have to have some knowledge, right? Certainly of what our file is actually storing. But if we, for example, if we know that our file is storing integer numbers, then that's something that we can work with, right? As long as we know what we're storing, of course, in the file, right? We're definitely going to have to know that. Then we have a way in which we can go directly to a specific byte in the file. And we'll see that come up in several of the code examples, but we have what are called seek functions that we can use. And the seek functions really can be used with both a file in binary mode or even a file that's not in binary mode. It can really be used with either. But here, what we would be doing is we'd be seeking to a specific byte, in particular, the byte where one of these numbers starts. So for example, if we wanted to read in the second number and only the second number, then what we could do is we could seek to byte number 4. Or if we wanted to read in the third number, then we could seek to byte number 8. And so the seek function, there's actually 2 different seek functions technically, although really when you're dealing with files, at least, there's really only one file position, but still considered good, good practice to use the right one depending upon whether you're going to do a read or a write after the seek. But it can take up to 2 arguments, because the second argument is actually where you specify where you're seeking relative from. But one thing that you can do is just reference the beginning of the file for the second argument. And then if you do that, then the first argument is basically almost like an array index in the sense of 0 and so forth. But with the added detail that we have to actually reference the exact correct byte number. So what you could do here is, like, let's say, for example, maybe we're gonna let the user have some control over this. So the user might be asked for a byte number or a record number, and that's the number that they want to read. So for example, 0 for the first number, 1 for the second number, maybe 2 for the third number, and so forth. The extra detail there, though, is that, for example, since each number is 4 bytes, we can't, just say 1, for example, to get to the second number, because we actually need to say 4 for the second number or 8 for the second number. But other than that, that's the idea in terms of how we can seek to the right position within the file. And so here's an example of how we could use that seek function. And here we're trying to simplify this to some extent for the user. So we could either tell the user something like enter 0 for the first number, 1 for the second number, or we could potentially just say enter 1 for the first number and then just account for that in our seek function. But here the idea is if we're doing it like this, where we're saying 0 for the first number from the user's perspective, right? 0 for the first number, 1 for the second number, 2 for the third number, that's fine. But we do need to account for the fact that each number is actually taking up 4 bytes physically in the binary file. So what we're doing here in this is a function call to this function called seekg, where the G stands for get. The idea with the first argument here is we're taking in that number, which is kind of almost like an array index number, right? But we're also multiplying that by, in this case, the size of an integer, because our records, meaning our values in the binary file, are all integers, which all take up 4 bytes. So just go ahead and take the number entered by the user, and assuming an integer takes up 4 bytes, although that could vary depending on the system, right? But assuming it's 4 bytes, then that's going to be multiplied by 4. So just whatever size of int returns, multiply that by number. And then the second argument here is you'll notice says iOS, which is that same thing that we saw when we talked about the flags, like input, output, binary. And then BEG, which is short for beginning. So what that just really means is you're seeking relative to byte 0, basically, right? Or the beginning of the file. There are other options that you can use there, which we'll eventually look at some of the different combinations. But for now, the convenient thing about beginning is that it means relative to the beginning, which in effect means that we can just treat the entire file in essence as an array, with the added detail that we do have to account for the actual individual bytes, right? So it's not enough to just say, seek G number, something like this, right? Because then the problem is if the user types in 1, which means that they want to read in the second number, then if you think about what that's going to try and do, because then you'd be saying 1 iOS begin, but think about what that's going to, we have to think about what that's going to do. So that would actually be going to here, actually here really. So that byte, right, that's highlighted right now is byte 1. So we would have a major problem, right? Because if you think about what's happening is we'd be seeking to that byte, and then if we follow up that seek statement with another with a read type statement. So because the idea is that first we would seek to the specific number that we want to read, and then right after that we could call the read function into, let's say we have maybe another variable here that we'll use for that. And similar to the things that we looked at previously, we could follow that up with the read function call using that value variable. But then we have to think about, well, what's actually going to happen? Well, unfortunately, we would be basically grabbing, those 3 bytes, right, plus this byte. And that's the 32 bits that we would be putting into the value variable. But unfortunately, that does not correspond to the number 1, because if we want to actually get the number 1, then we would need these 4 bytes. Or if the goal was to read in the second number, right, then we would want to get these 4 bytes. So we do have to be very specific about which byte number, but fortunately, regardless really of what type of data we're working with, this is a very, very generalized process. So all you have to do in this case is multiply this by the size of whatever type that you're working off of. Right? So for example, size of int or even really size of number would be fine too. But we do need to do that extra detail there. Because again, the whole idea was we were simplifying this a bit from the user, right? We didn't expect the user to necessarily be thinking in terms of increments of 4, because that's kind of more of a low level detail. But we do need to account for that in the actual logic of the seek function. So the user's input multiplied by the number of bytes for that type. As long as we do that, then we're going to be fine. So now, if the user types in 1, for example, that's going to be 1 times 4, assuming an integer, is 4 bytes on the system that we're running this on. So we're going to get the number 4, and then that means go 4 bytes over relative to the beginning of the file, or byte 0, which means we're going to seek, right? We're going to seek to here this byte and then read the 4 bytes that start there, meaning those 4 bytes. So we're going to read all of those that 32-bit value and bring that into that value variable. So now we just have successfully read the second number from the binary file. And so that's the basic idea. At least one way to use these seek functions. Again, The good thing about using begin here is it's kind of like an array with the added detail of taking into account the number of bytes. So that is important that we handle that detail as well. And then notice that right after the seek function, we just follow that up right away with a read, call to read. And we also do have a function called seek p, which means seek put. And the idea is that you can use that one right before a write statement. Now, at least for file streams anyways, there's only really one file position. So, I mean, technically it's all the same in terms of which seek you use, but it is, good practice to use the right one depending upon you're, about to do a write or a read. So before a read, we can do a seek G. Again, this was saying, seek to that byte number and then read the byte that's there. Whereas with seek P, we would normally pair that up with the write statement. So seek P would come right before a statement that's going to do a write operation. So we have, again, seek G as well as seek P. Both have the same setup in terms of parameters, right? So we saw that read and write have the same setup, right, in terms of parameters, and seek G and seek P also do as well. So seek P, again, is intended, right? The intended use is to pair it up with the write, whereas seek G is what we pair up with the read. They have the same, right, general arguments. Okay, so that's the idea. Another function that we have also aside from the seek functions is we have a function called tellg or tellp, and those functions will just tell you the byte number. So if you're just wanting to see that, or you're interested in that information, after you do, for example, a seek, you can print out the exact byte number that you're at, right? So if we do like a seek here, and then do like cout fobject.tellg, that's just going to print out the byte number that we're at. And then the idea is that a read operation or a write operation, in addition to doing the actual reading or writing, we know that it also advances the file position. Because in particular, if we seek to the second number, we said that you'd be seeking to byte number 4. which is the first of the 4 bytes for the second number. But since we're reading all 4 bytes, it means that then the file position is going to be up here. So, you know, if we did like another, for example, another TLG after this, right, then we're going to be at another byte position in the file, because the read operation itself causes that file position to advance. So TLG, again, we have seekg and TLG. TLG tells you the file position, and it's intended to be used with things like your seekg and read. And then we also have TELP or TELPUT, which does the same thing, but it's intended to be used with a seekp or a write type operation. So we're seeing in particular that things like seekg, TELG, and read, right, those kind of go hand in hand, and then seekp, TELP, and write, those 3 go hand in hand. So for both, right, both functions, that, you know, the P stands for put, and then for both of these functions, the G stands for get. So that's just going to, you know, print out again the byte number that you're at. And so that's how we now start to have a lot of control in terms of what we do, what we're actually wanting to do with these binary files. Because not only can we specify things like how many bytes we're going to read, but we can even control where within the file we want to read, right? Because we certainly might want to just go in and read one entry or one record without necessarily having to read every single thing, you know, that's in the actual binary file. And so we're seeing that by starting to combine these different things together, like the, you know, read and seekg or write and seekp, that really anything is possible. And so we looked at, you know, the basic idea in terms of our file. Now, regardless of what you're actually storing in your file, because here we were talking about an example of storing a bunch of integer numbers back to back, but anything is possible, right? We could be storing, for example, a bunch of characters. We could be even storing things like a student structure objects, meaning a bunch of those objects being stored back to back in the binary file. So anything is possible, and really, in the end, the way that we actually process the binary file is really not that much different, right, across different types. The main difference was that we know that if we're not dealing with a character type directly, we do have to go through that extra step of doing a cast to type char star. And I mean, we do have to think about, like we talked about with the seek functions, we had to use the size of operator here to correctly go to the right byte number. But really, other than that, right, the code is going to be very similar for a lot of it, regardless of what type of values that we're actually dealing with in our binary file. So again, it could be the file is storing a bunch of characters like letter A, letter B, letter C, letter D, in which case each record or entry is 1 byte, right? Because we have 1 byte or 8 bits for each character. It could be integer numbers like we were talking about up here. And it could be even something bigger than that, right? Like we're kind of hinting, it could even be that the idea is that each entry or each record in the file is actually a student structure object, where each record is going to have all the fields, right? Like the name and the ID number and the letter grade and the test score, the things that we saw throughout the structure chapter and the linked list chapter. Even that kind of thing is possible, because as long as we specify the right arguments with things like our calls to read and write or seekg and seekp, then really anything is possible, right? We can really work with any type of data values that might be stored in the binary file itself. But again, in thinking about the file, you really want to think of it in terms of bytes, because that's exactly what's happening when we talk about the read functions or the seek functions. It's all a matter of that fundamental question of where are you starting to read the data from, right? And then how many bytes are you going to read? So that's going to control what ultimately happens. And again, we can also see why, in addition to things like read and write, why we also need those seek functions, because in particular, we know that the read function itself does not specify where you're going to read from. Or likewise with the write function, we don't specify where we're going to write to. The idea being that whenever you actually call read or write, you should already at that point be at the exact position where you want to read from or write to. That certainly needs to already be known by the time you're actually calling the read or write function. Because again, in the read function, we don't specify, in the read function itself, we don't specify where we're reading from, but we do specify which variable, meaning which location in memory we're going to be bringing the data into. And we also specify with that second argument how many bytes we're reading. But it's really through things like, for example, the seek function that we can beforehand specify where, right? Where do we want to start reading from? So that's why we can control that by combining the seek functions with a call to read or write. And that gives us the ability to really do whatever we want in terms of how we process the overall binary file. So we could be storing numbers, but we can really be storing anything here. But again, that's how you want to think about it in terms of what's really going on when we talk about processing the contents of the binary file. So in this example here with the integer numbers, and of course this is scalable. I mean, the same idea if we wanted to add, 100 numbers in here, is whatever the user enters, right, you would just take their input, which from their perspective, they're thinking of it in terms of increments of 1, like 0 for the first number, 1 for the second number, and so forth. In reality, since each integer is usually going to be 4 bytes, right, we need to take that input from the user and then multiply it and then go to that byte. Because we always want to make sure when we're assuming we wanting to do a read, we want to go to the first of the 4 bytes for that number and then read all 4 of them, right? Whether it's this number or this number or this number and so on and so forth. And like we said before, because what can happen, if we don't settle that up correctly is we could, for example, like we said before, if the user enters 1, but we don't multiply that by size of integer, then you get into situations where you're doing stuff like reading the 3 bytes of this number along with the first byte of the second number, and that's not going to really give us the correct result there. So we just need to make sure that we're controlling that correctly through the combination of usage of the seek functions and things like the read and the write functions. Okay.